Alright, let's go. Number 10. The Rare Earth Hypothesis. Peter Ward and Donald Brownlee were paleontologists and astronomers at the University of Washington, trying to answer a much smaller question in the late 1990s: why did complex animal life take so long to appear on Earth? They weren't hunting aliens, they were hunting fossils. The standard assumption in astrobiology at the time was that if a planet sits in the habitable zone, with liquid water on its surface, life should eventually follow, and complex life should follow that. Simple math. Wet rock plus time equals biology. Ward and Brownlee found something else. The conditions required for complex multicellular life weren't common at all. They were absurdly specific. In their 2000 book Rare Earth, later expanded in peer-reviewed papers, Ward and Brownlee laid out a list: a large stabilizing moon, plate tectonics to regulate carbon, a gas giant like Jupiter sweeping up debris, a galactic habitable zone away from radiation-heavy regions, and a star that doesn't flare. Earth checks every box. Statistically, that shouldn't happen twice. Scientists tried to push back. Some argued microbial life is common, and that's what matters, not complexity. Others pointed to extremophiles surviving in conditions once thought impossible, arguing biology is more stubborn than Ward and Brownlee assumed. Neither argument addressed the actual claim. Microbial life staying microbial forever doesn't answer anyone's question. It just relocates the silence. If Ward and Brownlee are right, it means the version of you reading this, a creature with a nervous system complex enough to feel dread about its own cosmic isolation, might be the product of a chain of coincidences so improbable it happened exactly once in a galaxy of 400 billion stars. What are the odds that the chain that produced you was ever meant to happen again? The silence gets louder from here. Number 9. Habitable zone exoplanets, still no signals. The Kepler Space Telescope team, led by William Barucki at NASA Ames, launched in 2009 with one narrow engineering goal: measure the tiny dimming of starlight when a planet crosses in front of its star. A transit. A shadow. Nothing more. The expectation, going in, was modest. Find a few dozen planets. Confirm the method works. Instead, Kepler and its successor missions confirmed thousands of worlds, many sitting inside their star's habitable zone, where liquid water could theoretically exist on the surface. Then the search for signals began. And it found nothing. Not a whisper. NASA's own data, compiled through the Kepler and TESS missions and cross-referenced with SETI's radio surveys run out of Berkeley since 1960, now covers several thousand confirmed exoplanets. An estimated tens of billions of potentially habitable worlds across the Milky Way alone, and precisely 0 confirmed artificial signals across more than 60 years of listening. Explanations were floated immediately. Maybe civilizations use lasers, not radio, and we're listening on the wrong channel. Maybe they're too far away for a signal to reach us yet. Maybe they've already stopped broadcasting by the time we're capable of receiving. Each explanation quietly requires inventing a new, unverifiable excuse. And every excuse used so far has failed to survive contact with better instruments. If the numbers are right, there are more potentially habitable planets in this galaxy than there are seconds in your entire life, and not one of them has said a word back. Was anyone ever there to answer? Number 8. The Drake Equation's Wide Uncertainty. Frank Drake was a young radio astronomer at the National Radio Astronomy Observatory in Green Bank, West Virginia, preparing for a 1961 conference. He needed an agenda, just a list of talking points to organize the discussion. He wasn't trying to solve anything. The standard scientific approach to an unsolved problem is to break it into smaller, measurable pieces, multiply the pieces together, and get an estimate. That's exactly what Drake did with the number of communicating civilizations in the galaxy. The equation worked perfectly as an outline. As a number, it produced almost nothing usable. Drake's formula multiplies 7 variables, including the fraction of stars with planets, the fraction of those planets that develop life, and the fraction of civilizations that survive long enough to be detected. Depending on which published estimates you plug in, from researchers ranging from Carl Sagan in the 1960s to modern reassessments in the Astrobiology Journal, the answer ranges from under 1 to over 100 million communicating civilizations, right now, in the Milky Way. Scientists have spent 6 decades trying to narrow the range. Better exoplanet data narrowed the early terms. But the later terms, especially the fraction of civilizations that survive their own technology, remain entirely unconstrained. There is no fossil record for a civilization. There is no way to sample it. The equation was never built to give an answer. It was built to show you exactly how much you don't know, multiplied 7 times. If the true number is 1, it's you. What does that make the silence? Number 7. The zoo hypothesis. John Ball was a radio astronomer at MIT's Lincoln Laboratory in 1973, working on the same problem as everyone else in SETI. Why hadn't we heard anything? He wasn't trying to be provocative. He was trying to close a logical gap the field kept avoiding. The standard assumption up to that point was straightforward. No signal means no one's out there, or no one's close enough. Absence of evidence treated gently, as evidence of absence. Ball proposed the opposite. What if the silence isn't absence? What if it's restraint? In his 1973 paper, published in the journal Icarus, Ball argued that any civilization capable of interstellar travel or communication would almost certainly be far older and more advanced than us, and that such a civilization might deliberately avoid contact, the same way conservationists avoid contaminating an isolated ecosystem. He called it the zoo hypothesis. We would be the exhibit that doesn't know it's an exhibit. Critics called it unfalsifiable, and they weren't wrong. If the explanation for silence is they're hiding it perfectly, no experiment can disprove it. Other researchers noted the hypothesis assumes a single unified galactic policy when even one curious or reckless civilization breaking ranks would be enough to end the silence. That objection has never been resolved either way. If Ball is right, every radio telescope on Earth has been permanently, deliberately answered with nothing, by design, for the entire span of human civilization. Would you want to know why they're staying quiet? Number 6. The Fermi Paradox itself. Enrico Fermi was having lunch at Los Alamos National Laboratory in the summer of 1950 with fellow physicists Edward Teller, Herbert York, and Emil Konopinski. The conversation had drifted, half-jokingly, to flying saucers and interstellar travel. Fermi wasn't running an experiment. He was making small talk. The physicists worked through the numbers casually, the same way physicists can't help doing. Billions of stars, billions of years, plenty of time for at least one civilization to spread through the galaxy. The math clearly suggested we should have company. Then Fermi reportedly just asked, flatly, where is everybody? There's no formal 1950 paper. The moment survives mainly through a later account by Konopinski, published as an Los Alamos memo years afterward, and Fermi's calculation has since been reconstructed and refined by physicists including Michael Hart in a 1975 paper in the Quarterly Journal of the Royal Astronomical Society, which formalized the contradiction: the galaxy is old enough that colonization should have happened many times over, yet there's no trace of it anywhere. The explanations multiplied for decades. Interstellar travel is too expensive, too slow, too dangerous. Civilizations lose interest. Civilizations self-destruct. Every explanation solves the problem for exactly one hypothetical civilization and does nothing to explain why it would hold true for literally all of them, every single time, without exception. One unremarkable lunch conversation exposed a hole in our model of the universe that 75 years of physics still hasn't filled. Why does a single unanswered lunchtime question still have no answer? Number 5. The Great Silence Problem. Astrophysicists Sebastian von Horner and later Eric Jones at Los Alamos, working independently in the 1970s and 80s, were originally trying to model something practical: how fast a slow sublight colonization wave would spread if a single civilization launched generational ships toward nearby stars. The standard expectation was that interstellar colonization, without any faster than light travel, would take an enormous amount of time, long enough that it might explain why we hadn't seen anyone yet. The models said otherwise. Even at a fraction of the speed of light, with centuries of pause between each launch, one civilization could colonize the entire Milky Way in roughly 5 to 50 million years. Jones published this timeline explicitly in a 1981 paper in the journal Icarus, comparing it to the galaxy's age of roughly 13 billion years. 50 million years, against that backdrop, is not a long wait. It's a rounding error. It means even one early, moderately ambitious civilization should have reached every star system in the galaxy, including ours, an enormous number of times over by now. Explanations tried to soften the number. Maybe expansion isn't a priority for advanced civilizations. Maybe resources run out before colonization completes. But the model only needs one civilization, one time, in 13 billion years to succeed. Not a common outcome. A single one. The galaxy has had roughly 260 times longer than it needed to be colonized already, if anyone out there ever tried. So why does the sky look untouched? Number 4. The self-destruction possibility. Carl Sagan and physicist William Newman, working at Cornell University in 1981, were trying to estimate something specific for a SETI feasibility study. How long the average technological civilization survives after developing radio communication, since that lifespan directly determines how many civilizations should be detectable at once. The standard hope going into the Cold War era calculation was that once a civilization becomes technologically advanced, it also becomes wiser, more stable, and longer lived. Sagan and Newman's math pointed somewhere darker. If civilizational lifespan after developing communication technology is short on a cosmic scale, then almost no two civilizations would ever overlap long enough to hear each other, even if the galaxy were full of them. Their 1981 paper, published in the journal Icarus, modeled detectability against average civilizational lifespan and found that even a modest fraction of civilizations self-destructing within centuries of developing nuclear or comparable technology would be enough. Statistically, to explain total silence across the entire galaxy. Later researchers tried to challenge the pessimism, arguing nuclear war specifically hasn't happened yet on Earth, so the assumption might be too grim. But the model doesn't require nuclear war specifically. Any sufficiently destructive technological bottleneck, climate collapse, engineered pathogens. Uncontrolled artificial intelligence produces the same statistical result. You are currently alive during the exact narrow window this model says matters most, holding technology capable of ending the very broadcast you're part of. Is humanity still inside its own listening window, or already past it? Number 3. The Dark Forest Theory. Science fiction author and former computer engineer Lou Sixon was working on a trilogy that began with the three-body problem in 2008. Trying to solve a purely narrative problem, why would an advanced alien civilization choose silence over contact? He wasn't publishing physics. He was solving plot logic that later caught the attention of actual researchers, including NASA scientists who cited it in subsequent SETI risk discussions. The standard assumption behind decades of active messaging programs, including METI International's deliberate broadcast starting in 2015, was that reaching out is safe, or, at worst, neutral. Lou's model treated that assumption as fatally naive. In the dark forest framing, every civilization in the galaxy is a hunter in a dark forest, unable to know if any other civilization it detects is peaceful or hostile, and unable to risk finding out because the cost of guessing wrong annihilation is absolute and irreversible. The only rational strategy under those stakes is silence, or preemptive elimination of anyone who reveals themselves. Physicist and METI critic David Brin had raised nearly identical concerns years earlier, in papers dating back to 1983, questioning the safety of intentional transmissions. Astronomer Seth Shostak of the SETI Institute pushed back, arguing any civilization capable of interstellar attack would have already detected us through our decades of leaked radio and television broadcasts regardless. That counterargument doesn't resolve the theory, it just moves the deadline earlier. If the dark forest logic is correct, the silence isn't emptiness. It's a strategy every surviving civilization independently arrived at. If everyone capable of hearing us is also capable of choosing not to answer, what does our continued existence actually prove? Number 2. The Great Filter Hypothesis. Economist Robin Hanson at George Mason University was originally working on models of technological and economic growth in the 1990s, trying to understand why civilizations expand at the rates they do. He was not an astrobiologist. He came to this from spreadsheets, not telescopes. The standard reading of the Fermi Paradox up to that point treated every step, from simple life to intelligence to interstellar civilization, as roughly comparably difficult. A long chain of moderately hard steps. Hanson's 1998 essay, later developed into a formal working paper circulated through George Mason University and cited widely in subsequent astrobiology literature, proposed something colder. Somewhere along that chain sits one step so improbable it filters out nearly everyone who attempts it. A great filter. Hanson laid out the actual math, with over 100 billion stars in the galaxy, and no confirmed contact whatsoever. At least one transition in the chain from dead matter to galaxy-spanning civilization must be extraordinarily unlikely enough to explain the total absence of neighbors across the entire observable galaxy. The unresolved horror of the hypothesis is its uncertainty about direction. If the filter is behind us, some past step, like the origin of life itself, was the improbable one, and we already survived it. If the filter is ahead of us, something between where we stand now and galaxy-spanning civilization reliably destroys everyone who reaches this point, and we haven't hit it yet. Every fossil, every extinction event, every year humanity survives, is either proof we already beat the odds, or proof we haven't reached the wall yet. Which side of the filter are you standing on right now? One entry left. It's not a new theory. It's what all 9 of them collapse into. Number 1. The uncomfortable 2 possibilities. Every researcher named so far, Fermi, Drake, Hanson, Ward, Sagan, Ball, Brownlee, Jones, Liu, was originally chasing a separate, narrower question: plate tectonics, radio equations, economic growth models, fictional plot logic. None of them set out to answer the same question. They ended up there anyway. The standard hope, across 60 years of SETI funding proposals and public statements, was that better instruments would eventually settle this. More telescopes, more data. An answer, one way or the other. Instead, better instruments only sharpen the same 2 branches, without ever choosing between them. Every strand collected above, rare Earth's improbable conditions, the Drake equation's unconstrained survival term, Hanson's undirected filter. Sagan and Newman's self-destruction window funnels into exactly 2 mutually exclusive conclusions, laid out explicitly in Hanson's own 1998 framing, and repeated in nearly every serious astrobiology review published since, including a widely cited 2021 reassessment in the Astrophysical Journal by Jonathan Carrigan and Frank Tipler's earlier work at Tulane. Either intelligent technological life is so staggeringly rare that humanity is functionally alone in the observable galaxy, or something, a filter, a war, a self-inflicted extinction, reliably erases civilizations before they can be heard. No third option has survived scrutiny. Every attempt to propose one hidden signals deliberate silence. Faster than light travel we simply haven't detected yet collapses back into one of the original 2 under close analysis. Both answers mean the same thing for you, personally. You are either a once-in-a-galaxy accident or a temporary survivor standing somewhere on a timeline that has, so far, erased everyone else who reached this point. Which possibility would actually let you sleep at night? The universe was never confused about any of this. 10 separate teams of scientists working on 10 unrelated problems, chasing plate tectonics and radio equations and economic models and fossil records, kept arriving back at the same locked door. That's not scattered evidence. That's a pattern too consistent to be coincidence. We built the most sensitive listening instruments our species has ever produced, pointed them at 100 billion stars, and got back exactly the same answer every time. Nothing. The silence was never the absence of a signal. It might be the signal. If you want to see more videos like this, click the video on screen now.